Have you ever heard of a digital twin? It's this idea of creating a perfect virtual copy of something in the real world. But building one you can actually trust? That's a huge challenge. I mean, how do you go from a physical object to a mathematical model that's not just a good guess, but is provably correct? So how do you do it? In this explainer, we're going to walk through the foundational ideas of system identification, and we're guided by an absolutely fantastic tutorial from Dr. Nima Mahadian. By the end, you'll see exactly how we can build these models with real mathematical confidence.
All right, so here's our game plan. We're going to start with the bedrock, using real-world physics. Then we'll get real and see how these perfect models handle the messy stuff, noise. From there, we'll build out a formal way to think about our search, and we'll cap it all off by answering the big one. How do we know our model is the one true model? Let's dive in.
So where do we even start? Well, the most solid approach isn't to treat a system like some mysterious black box and just guess from the outside. No, instead we use the fundamental laws of the universe, physics, chemistry, you name it, to build our model from the inside out.
And this right here is our main tool for the job, the state space model. Now, I know this equation might look a little intimidating, but it's really just a super clean way to organize everything we know. That x vector, that's the system state, its internal memory. Think position and velocity. The u is the input. It's what we do to the system. And those matrices, F and G, well, they're basically the rule book that says how the state changes and reacts. It's the whole system, all in one neat package.
Okay, to make this real, let's think about a simple DC motor. The input, U, would just be the voltage we apply, and the state, X, could be the shaft's angle and how fast it's spinning. By using the laws of mechanics and electromagnetism, we can figure out the F and G matrices that perfectly define this relationship. This is the ideal scenario, a model built on pure physics. But reality is always a little more complicated, isn't it?
Yeah, here's the catch. Models that are based on pure physics are perfect. But the real world, well, it isn't. It's messy. You've got vibrations, friction, little fluctuations in power, all these imperfections we can't possibly model one by one. So we just lump all that uncertainty together and give it a name, noise. And it turns out not all noise is created equal. As you can see in this diagram, we've got to deal with two different kinds. First up, there's process noise. That's the W right there. This is stuff that actually affects the system itself. Think of a random gust of wind or some unexpected friction. Then you've got measurement noise, the V, which messes with our sensors. Maybe our thermometer is a little off, or our ruler is imperfect. Both of them totally cloud our view of what's really going on. So, this brings us to the big problem, right? Our model isn't perfect, and our measurements aren't perfect either. So if everything we can see is corrupted by noise, how on earth can we figure out the true state of the system that's hiding underneath it all?
Well, the solution to this puzzle is one of the most elegant and powerful ideas in all of engineering, the Kalman filter. Now, don't let the name fool you. This thing isn't just a simple filter. It's an optimal prediction engine. It's specifically designed to give us the absolute best guess of the true state, even when it's buried in noise.
The filter works in this beautiful, endless loop. First, it uses its model to predict where the system is going to be next. Then, it takes an actual measurement from the real world. Next, it compares its own prediction to that noisy measurement to see how wrong it was. And finally, this is the magic part, it uses that error to correct its internal guess, making it even more accurate for the next time around. It's constantly learning and self-correcting. So how does it pull off this magic trick? The secret is something called the Kalman gain. And the best way to think about it is as a trust slider. Just look at this visual. If our measurements are really noisy and unreliable, the gain is low. The filter basically says, nah, I'm going to trust my own prediction more. But if our model is the shaky part, the gain is high, telling the filter to pay really close attention to that incoming data. It's this constant, optimal balancing act between what it thinks and what it sees.
Now, the Kalman filter is amazing for a given model. But what if we don't even know the right model to start with? See, in system identification, we need a way to define the entire universe of possible models. We have to create a search space where we can hunt for the one that actually fits our data the best.
And this slide gives us the absolute perfect analogy for this: territory versus the map. A model set is the whole territory, all possible systems of a certain kind, like all second-order linear systems. But that's way too big to search. So a model structure is the specific map we lay over that territory, a coordinate system with parameters we can actually tune and optimize. It's what makes the search manageable.
This whole methodical process leads us to the most critical question of all.
Let's say our search finds a set of parameters that creates a model, and it works perfectly. How do we know it's the only one? Is it possible that a completely different set of parameters could give us the exact same result?
The answer to that question, the formal guarantee we've been looking for, is a property called identifiability. A model structure is identifiable if there's one and only one set of parameters that can describe the true system. It's the concept that makes sure our final answer is unique and that the numbers we find actually have a real physical meaning.
So how do we make sure our model has this property? Well, you lose identifiability when the model is just needlessly complicated. The slide mentions pole zero cancellations, which is just a fancy way of talking about redundancy. Think about a simple fraction. If you have a 5 on the top and a 5 on the bottom, they just cancel out. The same thing can happen in our models. To get that unique solution, we have to make sure our model is in its simplest form, with no hidden, redundant part.
And just like that, we've made it through the whole journey. We started with physical insight, using fundamental laws to build our state space model. Then we faced reality by accounting for noise, which led us to the amazing Kalman filter. We formalized our search by defining model sets and structures, and finally, we laid down the theoretical foundation of identifiability, which gives us that formal guarantee that our result is unique and meaningful.
So why does all this matter? It matters because we've built a rigorous framework of trust, taking us from a simple hunch all the way to a provably unique model. We now have the tools to create those digital twins with real confidence. So let me leave you with a question. What complex system is out there in your world, whether it's in engineering, finance, or even biology, that's just waiting to be identified?